So now let's take one more example, slightly more complicated than the previous example, and we'll introduce a couple of very interesting concepts using this example. So for example, if you look at the previous video, so we introduced the symbolic or the electronics representation of AND gate, OR gate, NOR gate, NOT gate and NAND gate as part of the example. So similarly, in this, we'll take a slightly more complex example, right? So imagine you have an automobile like a car. Many cars have a headlight warning system, which warns if the headlight is turned on unnecessarily. Again, this was very popular when the car battery capacity was low and people did not want to waste the car battery because the headlights run off the car battery and you don't want to drain the car battery. Modern cars are much more efficient and you even have daylight running headlights, but typical cars if you look at cars 10 years back, many cars had the headlight warning system. Even some modern cars have this. The objective here is if the headlight is turned on unnecessarily, it should warn. And even if the headlight is turned off mistakenly in tricky situations, it should even still warn you. So there are three basic things. Again, let's think about the problem itself, right? You have a digital logic circuit here, which either warns you, which either says 1 basically means it's a warning sign, 0 means no warning required. And this warning itself is fed into a LED, which is like a light that glows, right? This is there typically on your car dashboard, or it can even sound a small beep saying there is some problem with your headlight, please check it. Or basically the warning can be either because the headlight is unnecessarily turned on or it is not turned on when needed. In both cases, it should warn. And the warning itself can be shown to the driver either using an LED light in the dashboard or using some sound, right? So this warn digital signal will be given to an LED or a sound, again through using a digital to analog D to A converter, right? Depending on what you want to use it for. Now, what are the inputs? So we have understood the outputs of this system. It's a simple Boolean warn signal. What about the inputs, right? So first input that you need is the headlight on or not? So this H represents, it's again Boolean, just like all digital circuits. It is Boolean, which says whether the headlight is on or off. Is the engine on or off? 1 means on, 0 means off. Is it night or day? 1 means night, 0 means day. Now, how do we know that whether the headlight is on or not? So most cars have a small knob that you can turn to turn on the headlights, right? So that knob which you turn, typically which is there on the right side or the left side of your steering wheel. Suppose imagine this is your steering wheel. You have a knob either on the right side or left side with which you can turn it on. So whenever the driver turns on the headlight, there is an analog to digital circuit which takes this signal and converts it into a binary signal. Again, this is analog to digital because you're converting a mechanical rotation to a digital signal. Similarly, whether the engine is on or not. Imagine this is the engine, right? If the engine is on, there is fuel that is pumped into the engine and the engine is running. That's also a mechanical system. So the signal that the engine is on, which is again electromechanical to be more precise, there is an A to D circuit, analog to digital circuit, that takes the engine status right now and gives you whether the engine is on or not. Similarly, to determine whether it is night or day, you might have a light sensor. Okay, there are very cheap light sensors that you can purchase, which cost about 20 to 30 rupees or half a dollar. And you can have a light sensor which is placed somewhere in the exterior of your car, and it determines whether there is external light or not, right, outside the car. So this, again, here also you have a simple analog to digital circuit because it has to take the ambient light into consideration and convert it into a digital signal. So if you look at it again, we will not bother about the A to D circuitry part in this course or the D to A circuitry part. We mostly care about the middle part, which is the DLC circuit, the inputs and the output. So we have 3 inputs now and 1 output. Now let's draw the truth table. That's what we learned in the previous video, right? So H is the headlight on or off? Is the engine on or off? Is it night or day? Should we warn or not? So because there are 3 binary variables, there are 2 power 3 possibilities, 8 possibilities here. Again, this is something that we learned in discrete mathematics when we learned Boolean logic and how to draw truth tables. It's a very simple thing. If you're not sure of it, please check out our videos in discrete mathematics, especially with respect to Boolean algebra and Boolean logic. Now, when headlight is off, engine is off, and it is not night, which means it's day, you don't have to show any warning sign. Simple. When headlight is off, the engine is also off, it is night, which means my car is parked somewhere. It is night, but there is no engine running, there is no headlight running, so we don't have to show any warning. Now, imagine if the headlight is off, the engine is on, but it is day. So n equals to 0 means it's day. So in daytime, the engine is on. You don't have to turn on the headlights because there is ambient sunlight because it's daytime. So there is no need to show the warning sign. Next, look at this. The headlight is off, the engine is on, and it is night time, which means you're most likely trying to drive because your engine is on at night time without the headlights on. And that is extremely dangerous. So it should warn, the warning should be 1 because it is night time, the engine is on, and there are no headlights, which is extremely dangerous. You should never drive without headlights on at night, right? So this warning basically says there is something wrong. Please turn on your headlights, right? It doesn't tell you whether you should turn on or turn off. It just gives you a warning signal. Similarly, look at this situation, right? So here it says the headlight is on, the engine is off, and it is daytime. In daytime, if you have mistakenly turned on the headlight, turned off the engine, and if you leave the car as is, it will completely drain your battery. The headlight is not needed. So it should again show a warning sign saying the headlight, it basically shows the warning sign and you have to understand that, okay, hey, I have mistakenly turned on the headlight. Similarly, if the headlight is on, the engine is off, and it is night time. Whether it is daytime or night time, if the engine is off, you don't require the headlight to be on, right? Hence, same logic applies here. Next logic is the headlight is on and the engine is on, but it is day. Look at this. When you're at daytime, right? This is daytime. At daytime, you're running, the engine is running, which means you might be driving, and the headlight is also on. This is useless. Daytime headlight is not needed, right? So that's why we give the warning sign here. The last case here is the headlight is on, the engine is on, and it is night. You don't have to show any warning sign. So if you look at this truth table, this is slightly more complex because we have 3 variables or 3 inputs and 1 output. Look at this. And we have 8 possibilities here. Now, if I were to represent this see, we got the truth table here based on the logic. Okay, each of these cases we filled based on the logic. Now, given this situation, how do you write the Boolean expression for it? One way to write the Boolean expression is, there are many ways of writing the Boolean expression. One way is, you say W equals to, where all is W1? Look at this. These are the 4 cases where W equals to 1. So you say W equals to, look at this case. In this case, what happens? H is 0. That's why you negate H. E is 1. So you keep E as is. And N is 1. So you keep N as is. So when will this be? Look at this. When will this be 1? If H is 0, if E is 1, and N is 1. Again, here, there is a product here. There is a dot here. So what does this mean? This means if H is 0, and E is 1, and N is 1. Okay, I'm using the mathematical representation instead of using the programming representation. Remember, very importantly, that A dot B basically means A and B, and A plus B means A or B. This is what we learned in discrete mathematics in Boolean logic. So I'm using the same representation here. Okay, I am not putting the dot here explicitly, but it means that there is a dot. So W equals to 1 if H is 0 and E is 1 and N is 1, or The second possibility here is, look at this. This says h is 1, e is 0 and n is also 0, which is nothing but this. Look at this. The way I have written this expression is I have taken all the combinations. Look at this. There are 4 combinations here that result in 1. Each of these combinations I have expressed it here. Because h is 0 here, I have put negation of h or h bar. E is 1, so that's why I have placed e here. N is 1, so I have placed n here. Similarly, let's look at the next term here. H is 1, so I have placed h as is. E is 0, so we have placed e bar. N is 0, so we have placed n bar. Similarly, look at this. This will correspond to h, e bar, n. H, e bar, n. This will correspond to h, e, n bar. Very simple, right? So, what we have represented here is, each of these you can think of it as a product. Again, this is your product in mathematics. In simple algebra, this is product and this is sum, right? In Boolean algebra, product means and, sum means or. So what do we have here? We have a sum. Look at this. We have a sum of products, because this is a product term. This is a product. This is a product. This is a product. So we have sum of products. So this way of representing a Boolean expression using the truth table as the basis is called sum of products representation. So this is called as sum of products representation. Now, instead of writing this complex expression every time, can we write shorthand for it? So electronics designers have said, okay, instead of writing h bar, e, n, all of it every time, look at this. This is 1, 0, 0. This is 1, 0, 1. This is 1, 1, n bar, right? N bar is 0. So they said, instead of writing this complex expression, can we write it in a simpler form? So one of the ideas is, very simple idea. Look at this now, 0, 1, 1. Again, the order here is fixed, h, e, n. This order of input variables is fixed, right? Now, if you look at 0, 1, 1, if you interpret this as a decimal number, right? 0, 1, 1 corresponds to decimal 3. This is something you might have learned in your C programming when you converted decimal numbers to binary numbers and vice versa, right? So you can, instead of writing h bar, e, n, you can represent this as numeric 3. Numeric 3 here, remember that numeric 3 is binary 0, 1, 1, and the first one corresponds to h, the second one corresponds to e, the third one corresponds to n. Because this is 0, you write it as h bar. Because this is 1, you write it as e. Because this is 1, you write it as n. So given an expression like this, a product expression or a product term like this, you can represent it using a decimal number. Now you can write it as 3 plus 4 plus 5 plus 6. Please remember that this 3 is not the number 3. This is one way of representing this product term. This is not equal to 6 plus 5, 11, 11 plus 4, 15, 15 plus 3, 18. It's not that, okay? This is not simple mathematics that you learn in your 5th grade or 4th grade or 2nd grade for that matter. This is Boolean algebra. So one way to, so here each of these terms is a product term and you're doing sum of products. Another way of writing this is you say sum 3, 4, 5, 6. Okay, some people also write it as, instead of writing sum, they put the summation symbol here. So whenever you see any Boolean expression represented like this, W equals to summation 3, 4, 5, 6, convert this 3, 4, 5, 6 into the binary representation of these decimal values and interpret it like this. Now, very importantly, each of these terms, look at this, this term is a product term. This term is also a product term. This term is a product term. This term is also a product term. Each of these product terms are also called as minterms, right? Look at this. What are the minterms that we have in this expression? 3, 4, 5, 6. Again, this is just terminology that we are learning here. Okay, I'm introducing some simple terminology because everything else is simple Boolean logic that you learned in discrete mathematics, right? So the minterms that are there in the expression for W are 3, 4, 5, 6, and 3 basically means this. Similarly, 6 basically means this. Again, if you think about it, why are they called minterms? Let's think intuitively why they are called minterms. Because it's a product term. If you have 3 binary values, right, whatever is the minimum of them is the result. Imagine if you have three terms, A, B, C. It's a product term, right? Look at this. If all three of them are 1, look at this. They're basically these two possibilities. If all three of them are 1, the minimum of A, B, C is also 1. And A and B and C is also 1. If any one of them is 0, let's assume B equals to 0. Let's assume. Then A and B and C will be equal to 0. And the minimum of 1, 0, 1 is also 0. The term minterm, the name minterm came into existence because a product or a logical AND of all these is equal to taking the minimum of all of them. Okay, that's why the term minterms. Okay, simple. Now similarly, so this is one way. Again, remember that this is a very concise way. Instead of writing this complex expression, we have represented the W. Remember, I can just represent W using these 4 minterms as the summation of these 4 minterms. It's a much more concise representation of presenting and understanding this Boolean expression. It's a very simple way. Instead of writing this complex thing, it is just a notation to simplify things, right? So just like sigma is a symbol to simplify or to concisely represent summation, similarly, this is a concise way of representing it. So given that we have some basic understanding of sum of products using minterms, let's understand a very simple question. Why do we care about representing things using minterms and as sum of products? There are basically a couple of advantages. One obviously is it's a much more concise way, much more crisp way, much more shortcut way, right? It's like a short form of representing the Boolean expressions, number one. Number two, if you notice, when we represent it as sum of products, all you need is basically 3 logic gates. You basically need 3 logic gates, right? We have seen logic gates in the previous video, right? You just need AND gate, OR gate, and NOT gate. Just by using chips that contain AND gates, OR gates, and NOT gates, you can express any Boolean expression now. Look at this. Whatever is your set of inputs and whatever is your output that you want to model, you just write the sum of products. The moment you write it as sum of products, you can very easily translate that expression using chips which contain AND gate, OR gate, and NOT gate. I'll show you an example for this problem in just a few minutes. Very importantly, in this video, we have just introduced the concept of minterms and sum of products. There are related concepts called as max terms and product of sum, right? So there is an alternative representation wherein you represent using product of sum and max terms. These are concepts that we will learn in much more detail in future chapters in this course. So there is a whole chapter called Boolean expressions where we will learn this in a lot more detail. Here I'm just providing you a high level overview and introduction. So there are other concepts called as canonical form, minimal form, etc. Don't worry about these concepts. We have a whole chapter little later in this course called Boolean expressions where we will cover all of them in much more detail with some example problems, right? So remember, this is what our W is, right? We have 3 inputs, H, E, N, and W is our output for our headlight warning system. Let's not forget the physical problem that we are solving. Now, if you notice, we can design the whole circuit. This is how you can design the whole circuit. Remember, W is H bar E N plus H E bar N bar plus H E bar N plus H E N bar. We have already shown this earlier. I've just copied this and pasted it here. Now, if you have to design a circuit, as I just mentioned a couple of minutes back, all we need is AND gate, OR gate, and NOT gate. So let's actually design this. Imagine that my ADC, my A to D converter, is giving me the H value here, the E value on this wire or connection, the N value here, right? So I take this connection and I place a NOT gate here. So what do you have here? This line now represents H. This line now represents H bar, right? This line represents E. Whatever is the value of E, the same value I can find on this wire, right? So this, because I'm passing it through a NOT gate, so here I can get E bar. Okay, so let me show this. This is E bar, this is H bar. Similarly, this is N, and here I get N bar because I'm passing N through a NOT gate. Now look at the terms that I need. Overall, what is the first term? I need h bar en. It's a product, which means I need a logical AND gate. What are the inputs to the AND gate? There are 3 inputs to the AND gate, right? So look at this. I'm connecting h bar here. Look at this. This h bar I'm providing as an input here. That's why I've drawn a thicker point here. This is E and this is N. So I take a wire, connect from here without touching any other wires. Again, I can't draw a 3D diagram here. So I'm only touching this wire, this blue wire which is there. I'll touch it to H bar. I'll not touch it to any other wire, and I'll connect it to the input of the AND gate. So what are the inputs to the AND gate here? H bar, E and N. So what are you doing? You're doing logical AND of all of them. So what do you get as output? H bar, E, N. The first term you get as an output of this AND gate. What is the second term here? H, E bar, N bar. So let's look at this. This is also an AND gate. Again, I didn't draw it perfectly, but this is an AND gate, right? It's simple. This is an OR gate. Remember, this is an OR gate. This is an AND gate. This is also an AND gate, right? What are the inputs to this AND gate? H, E bar. Look at this. This is H. This is E bar. Look at it. Where is it connected? It's connected to the E bar line. So where is this connected? This is connected to N. So you're taking H, E bar, N, and you're passing it through AND gate. So what do you get? You get H, E bar, N. Similarly, see, H, E bar, N is the second term here, right? It is the second min term here. Similarly, the third min term that you have is H, E bar, N. Same thing, you connect H, E bar, N. The last one, you connect H, E, and N bar. So these 4, look at this. We are just using NOT gates here. Why do we need to use the NOT gates? Because I need H bar, I need E bar, I need N bar. So we are using the NOT gates given that the inputs we get is H, E and N. Since we need the NOT of it, we are using the NOT gates. We are using the AND gates to compute the minterms themselves. And finally, what do we want? We want to compute the OR of all of them. So now we have an OR gate which takes this, and this as input. And what is the resultant that you get here? The resultant that you get here is H bar En plus H E bar N plus H E bar. Also, this should be H. This is H E bar N bar. I'm sorry. So there is a small mistake here. Let me correct it. There is a small mistake that I've made. Again, it's a little confusing when I drew it. So it is H E bar N bar, right? So this should have been N bar like this. Okay, small typo there. Let me just correct it. Okay. So this is H E bar N bar. Cool. So H E bar N bar. This is H E bar N. So this is H E bar N. Yeah, this line is N, this line is N bar. So you have to be slightly careful where you are connecting just to make sure that there are no errors. So finally, what do you get? Your OR is, this is your first term, this is your second term, your third term, your fourth term. So what you get as an output is W. Look at it, by just using logical AND gates, an OR gate and NOT gates, we have constructed the whole circuit. Now the beauty of this Minterms approach, the beauty of representing everything using Minterms and sum of products is, given any complex, again remember the logic here is non-trivial. We drew the, remember given the real problem, we have drawn the truth table, we have come up with the Boolean expression, and now we have converted the Boolean expression into logic gates. Now wherever I need AND gates, I can just use the chips just like the way I've shown you in the previous video. Right? Same concept. There are also chips which will give you OR gates. There are chips which will give you NOT gates. Okay. Now your question could be, hey, this AND gate, I have 3 values here, but the AND gate that we have seen in the chip only has 2 inputs. Look at this. If you want to create an AND of 3 values, right? This is an AND of 3 values, right? Imagine you don't have a chip which takes 3 inputs. How do you design it? It's very simple. You take 2 inputs. Let's assume this is A, this is B, this is C. What you want is A, B, C. How can you do it? Imagine if you have only AND gates which take 2 inputs, A, B. So this is A, B. This is your C. One thing that you can do here is you can take this A, B. You can pass it through one more AND gate. What do you get now? The input here is A, B. The input here is C. So you get A, B, C here. So if you do not have AND gates that take 3 inputs, but if you have AND gates which take only 2 inputs, Okay, because we have seen that circuit diagram just a while ago, right? So let's see that. Okay, look at this. This is what we saw in the previous video. In this video, if you notice, each of these AND gates in this chip 7408 take only 2 inputs and generate one output. Imagine if you are using the 7408 chip for this problem, because if you notice, all the ANDs require 3 inputs, but your chip 7408 doesn't let you do that. So then what do? You just create a very simple solution where instead of this is equivalent to, remember that this is equal to this circuit, right? If you have AND gates which only take 2 inputs, you use 2 AND gates, right? And you can still get A dot B dot C. This is how you can do electronic circuit design. Again, this section is only a very basic introduction. We'll understand much more about it. We'll understand about max terms, product of sums, minimal forms, canonical forms, all of it in the future chapters. I'm giving you a glimpse of what we're going to see in the future.